Good morning, champs. Welcome to functions of several variables, partial derivatives. Until now, we looked at functions of one variable, curves in the xy plane. But when a function depends on two variables, like f of xy, we get a surface in 3D. Changing x nudges the surface one way, changing y nudges it another. We want to measure the rate of change when exactly one variable moves and the other is held fixed. That's a partial derivative. Definition time. For a function f of x and y, the partial derivative with respect to x is the limit as delta x goes to 0 of f of x plus delta xy minus f of xy divided by delta x. Read that as vary x freeze y. Similarly, with respect to y, the limit as delta y goes to 0 of f of xy plus delta y minus f of xy divided by delta y, vary y, freeze x. Geometrically, you're slicing the surface with a plane parallel to either the xz plane or the yz plane and taking the slope of the slice at the point. Let's warm up with a classic f of xy equals x squared plus y squared. Then the partial with respect to x is 2x, and the partial with respect to y is 2y. At the point 1, 2, that gives f sub x equals 2 and f sub y equals 4. Interpretation. If you take a tiny step only in the x direction, f increases about 2 times your step. If you step only in the y direction, it increases about 4 times your step. Those are the instantaneous slopes along the coordinate directions. If you drew the tangent lines on the surface at 1, 2, one would tilt with slope 2 along x, the other with slope 4 along y. A spicier example, f of xy equals x squared y plus 3xy squared. Differentiate holding the other variable constant. With respect to x, 2xy plus 3y squared. With respect to y, x squared plus 6xy. If you go to second order partials, you get f sub xx equals 2y, f sub yy equals 6x, and the mixed partial f sub xy equals 2x plus 6y. That mixed partial tells you how the x slope changes as you move in the y direction, and under mild smoothness, f sub xy equals f sub yx. Here's the geometric big picture. Think of the surface z equals f of xy. The two numbers f sub x and f sub y at a point are the slopes of the best local linear approximation along x and along y. Put them together and you get the gradient vector, bracket f sub x, f sub y bracket. The direction of steepest ascent and the magnitude of the steepest slope. That same pair defines the tangent plane. Z is approximately f at open parenthesis x0, y0 close parenthesis plus f sub x at open parenthesis x0, y0 close parenthesis times open parenthesis x minus x0 close parenthesis plus f sub y at open parenthesis x0, y0 close parenthesis times open parenthesis e minus v0 close parenthesis. For our paraboloid at 1, 2, that linearization is z approximately 5 plus 2 times x minus 1 plus 2 times y minus 2, 4 times I minus 2, which simplifies to 2x plus 4y minus 5. Key takeaways. 1. Partial derivatives measure change along one coordinate direction while holding the others fixed. 2. Compute them by treating the other variables as constants, just like single variable rules but with the other variable frozen. 3. Mixed partials capture interaction between directions. 4. Together, the partials define the tangent plane and the gradient, which we'll use constantly in optimization, Jacobians, and the multivariable chain rule. Up next, we'll assemble these partials into the Jacobian matrix, the ultimate linear snapshot of how a multivariable function transforms space.